Okay, hi guys. This is the specific heat of brass procedure page. You don't have to copy down the procedures. So I'm going to go through the pre-lab with you a little bit. This is in relation to our discussion on heat and temperature and specific heat. To change the temperature of a solid, you have to add energy. And the amount of energy you add depends on the temperature change you want to make, how big the object is, how much mass it has, and then kind of the internal, intrinsic characteristics about the material. Each substance has been researched many times over the years under standard conditions, and there are tables and tables of specific heat capacity that are listed for different kinds of metals, different kinds of substances. This is the equation that's in your chapter as well. Q for heat, Cp for specific heat capacity, M for mass, and delta T, of course, for change in temperature. The specific heat does vary depending on what temperature conditions you're taking your results in, but it won't affect us that much. Q for heat was measured in terms of calories. It used to be something called a caloric. It was some sort of substance you had inside of you. Of course, we now know that heat is a form of energy, and we don't use calories, except in the United States to talk about food calories, but we don't use them in science. We use the joule, and I actually would like you to use 4.184 joules per gram degrees C. That's specific heat capacity of water. Again, it's a very specific temperature range. You're supposed to go from 14.5 to 15.5 to get a calorie, the exact definition of a scientific calorie, but we'll just assume that we're close enough for government work. We've talked about this concept that two different objects, when you put them together for long enough time, they will come to the same temperature, thermal equilibrium. The warmer object will give off energy and the colder object will absorb the energy. And we're going to use, or I did use, a method called calorimetry, measuring the heat. It's also used to find the heat calories. That's in something called a bomb calorimeter, B-O-M-B, and that where they literally burn up food. What I did is I put a piece of metal, a brass mass, into water and brought it to boiling, which was not 100 degrees in our particular case, and then transferred it to the calorimeter to see how much a known volume of water, how much that temperature increased. So that was the background information I wanted you to read. On the back is a very tiny data table. Remember, I only did one trial, so there's no averaging required. The mass of the object was 200 grams. The milliliters of water was 50 that I put into the styrofoam cup in the calorimeter. The initial temperature of the water, or T1, was 20.8 degrees. And the final highest temperature of the calorimeter, when I put the mass into the water, came out to be 39.6. I might not have waited quite long enough, but that's the way it goes. So the next part of this is a series of questions asking you to do calculations. I think it'll be easier to do those on a separate piece of paper, so that's what I'm going to do for you. So question number 1 was, what was the change in temperature of the water in the calorimeter? And so to calculate that, I simply have to subtract the final temperature of the water from the initial temperature of the water, and that was 39.6. So you can just copy this down if you would, please. 20.8, and so the change in temperature of the water, unsurprisingly, we put a piece of hot metal in the water, it went up 18.8 degrees C. Some of you may know that Native American cultures, they could cook their food in straw baskets, and that just doesn't seem to make sense, right? We have metal pots and pans, and what they would do is they'd heat up rocks in their fire and then put those rocks, hot rocks, into the porridge or whatever they were cooking in their straw baskets, and the basket wouldn't burn, but the food would cook. Pretty cool. The next question is find the change in temperature of the brass mass. And on the data table and on the lab, it says take that final temperature of the brass plus the water and subtract 100 from that, assuming that the boiling point of the water is going to be 100 degrees, which unfortunately it was not for us. It was slightly lower, so it was actually 98.2, whether that's an artifact of a miscalibrated thermometer, the weather, whatever else was going on, I don't know. So when you do that, 39.6 minus 98.2 gives you a negative number, right? Remember, the water gained energy, the mass lost energy. That's signified by the negative sign. So it went down 58.6 degrees. At this point, we're going to start making use of our equation. So again, Q is equal to specific heat, and we're using specific heat of water, times the mass of the water, times the change in temperature of the water. And we're going to assume that the specific heat of water is 4.184 joules per gram per degree C. And then the mass of the water, well, it was 50 milliliters. We're going to assume the density 1 gram per milliliter, so 50.0 grams. And we already calculated the change in temperature, 18.8 degrees C. You're going to tell me how much heat in joules the water gained. Okay, and number 4, you're going to assume, rightfully so, that whatever heat the water gained is equal to the heat that the brass lost. Okay, so this number is going to be the brass lost value, so it's going to be a negative, but it's going to be the same numerically. And then using this value, we're going to rearrange our equation up here and solve for specific heat. So we need to divide both sides by the mass times change in temperature. So for the second part of part 4, you're going to have CP brass is equal to Q brass, which should be negative, over mass of the brass, which is 200, times the change in temperature of the brass. So that is, this is 200 grams, and this was the negative 58.6 degrees. So you can see your negative signs are going to cancel, so you can kind of ignore them, and you're going to get the specific heat of brass. Again, this is joules, this is grams, this is degrees, so the units for specific heat are joules per gram degree C. Question number 5 asks you to find the absolute error. Error is the actual value you got in the lab minus the theoretical value that you're supposed to get. And we find the absolute of that. So whatever number you get in 4 minus the theoretical, which it's in the lab paper, 3.80 joules per gram degree C. So this is your error. And then number 6, the percent error, because this doesn't mean anything until you compare it to something else, is you take your answer to number 5, the absolute error, and you divide it by what it should have been, theoretical, and of course times 100. So the absolute error, this answer goes on the numerator. The theoretical is a 0.380, and you will get your percent error. And this one didn't turn out so great. Again, I probably rushed it a little bit. Hopefully this isn't too hard for you to follow along. Email me with any questions. Take good care.